It's a great pleasure to have Amir Levinson give today's seminar. Amir did his degree from Ben-Gurion University in 1992. He got his PhD there, and then he did postdocs at Caltech and Cornell, and then since 1997 he's a professor in Tel Aviv University. Amir is very well known for his work to do with spinning black holes. I would say observational appearance of spinning black holes, both in gamma ray bursts and in AGNs. So he's one of the people who developed what is now a standard model for gamma ray production in AGNs. And he's also done some, what I would say is now the standard canonical work on shock breakouts and on the physics of shock breakouts from stellar surfaces, relativistic shock breakouts. I guess today you will tell us about more about the physics of jets and how jets are produced and what they do. Please, go ahead.
Okay. Thank you, Yuri. So I guess I should share the screen, right? Second. Okay, so just 1 second. Good. So so we had two excellent talks previously by Luigi and Paolo, discussing observations and phenomenology of blazars. And in this talk, I'd like to focus on what I see as some fundamental issues in the theory of blazars from more fundamental point of view. So more specifically, I'd like to do two things. First, to discuss some recent progress in modeling of general dynamics and also microphysics related to blazars from first principles. And the other thing I'd like to try and do is to elucidate the challenges, because I think it's important to understand the challenges in order to try and make further progress. So let me, just a second, okay. Let me first make a quick summary of what we heard in the previous talks. And I think that the main impression one gets from looking at the data and listening to these talks is that blazars are extremely complex systems. And they show a diverse range of behaviors, and even a single source changes its behavior over time. And this is not surprising given that these are extended systems which are located in pretty complex environments. However, they do seem to have some common characteristics, and I'll summarize them here very quickly. And in my view, even explaining these characteristics from first principles grossly will be a tremendous challenge. We are not even there yet. So, and I do think that there has been some progress, even despite the complaint by Felix last time. Okay, so one of the characteristics, what people like to call defining characteristics of blazar, is non-thermal emission. This is actually common to all high-energy astrophysics systems. This readily implies that these systems are far out of thermodynamic equilibrium, and there must be some process generating these very broad particle distribution functions. And I'll discuss some studies. The other thing is high efficiency. Now, by high efficiency, I mean that at least 10% of the estimated jet power is tapped to produce the emissions that we see. And according to some studies, the efficiency is might be even higher, 20–30%. This suggests that a substantial fraction of the jet bulk energy, actually jet magnetic field, should dissipate. And the last property is rapid variability. So most blazars or many blazars exhibit rapid variability, maybe not as extreme as this or Sparks 2155, but nonetheless sufficiently rapid or with duration as short as, let's say, horizon scales. So this with combination of other data, to me at least, suggests that dissipation must occur pretty close to the engine. By pretty close, I mean hundreds to thousands of Schwarzschild radii. So there are models that can produce rapid variability by other means, but I think that the data we have suggests that the dissipation must occur not too far out. And this is, as I'll suggest, this is a challenge actually. We also have indications for high energy and very high energy emission for so-called misaligned blazars, notably MIT7. And also here we see rapid variability. And since these sources are not beamed, it implies that the emission must come from the vicinity of the black hole probably. And I will discuss some possibilities studied very recently, like maybe flaring states of the accretion disk, spark gaps in the magnetosphere, etc. Okay, now I think that Paulo have shown a version of this slide, at least this figure in his talk. This shows a general scheme that we all have in mind. There is like an accreting black hole producing this relativistic jet somehow. Jet somehow dissipates, maybe through shocks, maybe not, and release the emission. And I think this scheme is quite good, but as I will suggest, it's actually more involved than this simple. And in particular, I think that what we have to keep in mind is that these monsters, these systems are multiscale systems. And this is, in my view, is the greatest challenge. And by multiscale, I mean that there are global scales on which, let's say, accretion and jet formation and dynamics occurs. And then there are microscopic scales on which energy dissipates. And we still have no idea through which channels. Could be shocks, reconnection, turbulence, shear flows. All of these possibilities have been discussed in the literature and mentioned in talks, and maybe triggered by instabilities. But the important thing is that these scales are not separated. Otherwise, our job was actually much easier. They are somehow interlinked. And by interlinked, I mean that the global dynamics and conditions in those systems probably dictates which of these dissipation channels might be at work, or maybe a combination of those. And on the other hand, the dissipation process and the radiation can feedback on the global dynamics of the system. So the question is how these scales are connected. And of course, you would like to have some sort of simulations that resolve all scales. I will show the multiscale, typical scale separation, in these systems in a minute after I will introduce some parameters, but as I'll show, this is impossible. So actually what you need is, and I know that people are trying to do that, is to find ways to somehow connect this microscale to the global scale of the system. And this is, in my view, is probably the biggest challenge in this business. And I'll show in the last part of the talk, I'll show some examples, specific examples. Now, I think we are in the last, let's say, decade or two, we are in the era where people are studying these processes from first principles, what some people like to call modern approach to high energy astrophysics. And so this goes way beyond the traditional phenomenological approach where you assume some components, maybe one zone, several zones, and you invoke some ad hoc particle distribution function to compute emission. So here people are actually trying to understand how these particle distribution functions are formed, what are the limitations, what are the conditions required in each process. And at the same time, there are also studies of the global dynamics. And most of these studies are heavily based on state-of-the-art numerical simulations, even though analytic approach is very important to get some insight into the numerical data. But these are essentially great tools, but I think that we have to keep in mind the limitations of each method. And unfortunately, I think it's not sufficiently well appreciated or recognized by many. And the reason why we need this is not only to understand if our results are meaningful, but actually also to guide us how to make further progress. So let me give some example by what I mean. And then I'll also use this example to indicate the topics that I would like to discuss in the rest of this talk. Sorry. So I'm going to show you here a very typical GRMHD simulations. It's 2D in this case. It's high resolution. That's what a bit different about it. But it's typical. There are hundreds of such simulations in the HD simulation bank. And I will get back to this simulation shortly when I introduce some parameters, but what I want to actually focus now on is to identify some features that are used for my argumentation. So this simulation typically start with an initial state, which is shown here. There is a rotating black hole at the center. It is initially surrounded by this big torus. It's big fishbone torus. And it's magnetized. So usually people invoke for convenience colloidal magnetic loops, as you see here. These are the magnetic surfaces. And then you let the system evolve, either in 2D or 3D. And you can see what happens here. So let me just quickly say, on the left here, in this move, you see the density in the system. And on the right, you see the so-called beta parameter, which is essentially the ratio of the kinetic energy to magnetic energy. So blue color here means magnetic dominance. So let me show the movie, and you see there is some delay during which the torus develop the viscosity by MRI probably. And then you can see some quasi-periodic behavior. I will talk about this later, but what actually I want to show now is the following. First, this kind of simulation demonstrates that we can actually form a self-consistent jet. So you see the flux tube penetrating the horizon. And you can easily show from the data that there is a Poynting flux going along these field lines to infinity. So this is a jet. And we also see that the inner region of the magnetosphere, which is painted blue here, is highly magnetized. It's actually what's so-called force-free, in the sense that the dynamics of the plasma is not very important. So that's what we know. But what we don't know actually is how magnetized it is. And the reason we don't know that is because in all the simulations, the magnetization actually, or if you wish, the density is set to some floor value in order to avoid crashing of the simulation. So this is not a problem if the only thing you want to study is the dynamics of jet formation. That's fine, because it only needs to be magnetized, sufficiently magnetized. But it is a problem if you want to study other things, like, let's say, emission from this region. And I will discuss a specific example in a minute. And so this simulation doesn't tell us how the plasma is actually supplied to the inner magnetosphere and to the jet. And of course, what's the composition then? It also doesn't tell us how magnetic energy dissipates. I'm showing here only a small window of the simulation to focus on the inner region, but if you look at the entire simulation domain, at least in this case, you see the jet to be pretty stable. We don't see any evidence for any instabilities. So it doesn't show us how the dissipation occurs. You could argue that maybe there is insufficient resolution, maybe the simulation box is too small, and these things will be studied in the future. Also, it's actually, this initial setups in those simulations is pretty limited. So it can only probe certain accretion regimes. For example, as far as I know, up to now, it's very difficult to actually study thin accretion disks like CDY-Initiative due to lack of resolution. So there are some limitations. We also have missing physics. For example, there is no cooling in the simulation, and there is no macrophysics that determines the electron temperature in the accretion flow, etc. So it's clear that we must find some complementary way to answer some of these questions. Okay. So what I want to discuss in the rest of this talk is several topics. I will start from the accretion flow itself, and we'll show these. I'll go back to the simulation, and I will show that the results suggest that we might actually have flaring states during mud accretion states that might actually emit high energy emission. I will then move on to discuss the issue of plasma injection in the magnetosphere. And I will show some recent results of GR, general relativistic peak simulations. This is a new tool developed by some people, which allow us to study the microphysics of the global magnetosphere with some limitations. And finally, I want to discuss the dissipation of the jet itself. Okay, so this is the plan. So before doing so, let me just introduce some key parameters in this business. So I'm using mu to measure mass in units of the proton mass, which depends on composition. Length scales are measured in units of gravitational radius and power in Eddington units. And so the two important parameters in the business of rotating magnetospheres, let it be pulsars or black hole, is angular velocity and magnetic field strength on the horizon or the stellar surface. And in the case of black holes, the angular velocity of magnetic surfaces is related to the black hole angular velocity. But there is one important parameter, which is a combination of these, which is a density scale, which you see here. It's known as the Gulick-Julian density. And its meaning actually is it's the minimum density required to screen out the magnetosphere and establish a force-free state, or if you wish, activate the system, in our case, the black hole. So you somehow need to supply continuously this value, at least, to keep the black hole activated. And the density in those systems is commonly measured as a multiplicity of this density scale. So I'll be using this kappa throughout, as you will see. Now, there is one key parameter in this business, which has been introduced already in previous talk by Elena in the context of the Crab Nebula and others. And this is a magnetization parameter. It actually gives the ratio of the Poynting flux to the bulk kinetic energy of the outflow. And you can actually scale it using the parameters I mentioned. And it can actually be a very large number in those systems. It depends on this multiplicity mainly, also some on the composition and temperature, but mainly on this multiplicity. And at low multiplicity, it comes to be very large. Now, this parameter controls both the jet formation process and perhaps dynamics on the one hand, and also the microphysics on the other hand. So for example, to get extraction of the rotational energy by magnetic fields, you need the value of this parameter to be very large near the engine. On the other, to get effective dissipation in shock, you need this value to be smaller than, let's say, 0.1, and to have efficient shock acceleration, at least in the relativistic regime, you need the value of this parameter to be smaller, even smaller than these values, depending on composition, as we've heard in, if I remember, in the talk by Martin, for example. This condition can be alleviated in non-relativistic shocks. And you can already see that if shocks are to be the dominant dissipation channel, you somehow need to reduce this sigma from very high values near the source to low values further out. And the question how you do that. So I'll go to, I'll be discussing this later in the talk. On the other hand, dissipation through reconnection or turbulence favor large values of sigma. And this seems to be more natural for Poynting flux dominated jets. And this is partly the reason why many people actually prefer these dissipation channels in these situations. However, they have their own issues, as I'll suggest. Okay, so before I move on to the first issue, let me just show the scale separation, typical scale separation. So in collisionless plasma, there is one important scale, which is called the skin depth. It's actually the inverse of the plasma frequency. And this is a scale on which, as I mentioned, energy dissipates. So just to get an idea, in case of reconnection, for example, this is roughly speaking the width of the current sheet, of the reconnecting current sheet. In the case of collisionless shock, this is roughly the width of the shock transition layer, etc. So if you want to study dissipation of these systems, in detail, you need to resolve this scale, and every peak simulation must resolve this scale to get meaningful results. Now you can calculate the ratio of the gravitational radius of the black hole to the skin depth. It comes out to be a pretty large number. It depends on the multiplicity and temperature, but roughly speaking, it ranges for about 10,000 in spar gaps to millions and even billions in dissipation region in the jet itself. So you see that if you want to try and do some self-consistency simulation that encompasses all scales, you need a huge dynamic range, and this is actually currently infeasible. So people are trying to find ways out of this. And just to get an idea, in most peak simulations, the one I'm familiar with, either of reconnection or shocks, the dynamic range is, I don't know, hundreds, maybe thousands in very big simulations. So it's much, much smaller than what we expect in reality. So again, I'm coming back to the question, how these scales are, how these microscopic systems are connected to the global system. Okay, let me move on now to discuss the first issue. So I'm showing again the simulation I started with, and I want to focus now on the dynamics of this accretion process. So let me run the movie. Now, sorry, just a second. Let me just mention that what I'm showing here is 2D simulation, high resolution 2D simulation, but there is an extreme resolution 3D version by Riperda and collaborators, a very recently published paper, which actually shows the very same behavior with some differences, but overall the same behavior. And what we see here again is that once a mud state is formed, and a mud state is formed once sufficient magnetic flux is being advected in the black hole, the magnetic stress consequently, as you can see here, ejects the inner disk, and then it forms this this forceful magnetosphere. So I'm showing here 3 snapshots. What happened to the movie? Sorry. I'm showing here 3 snapshots from one cycle of this movie. And you can see there is an intense accretion state initially, and then when sufficient flux is advected, the inner disk is ejected, and then a current sheet forms in the equatorial plane. And this current sheet, what it does, it actually reconnects magnetic field line and exhausts the magnetic flux of the open flux tube penetrating the ergosphere. So eventually, the outer material is able to push in, and the cycle resumes. Now, this current sheet actually dissipates a substantial fraction of the accretion energy. So during this match state, we expect to have emission from this current sheet. And the question is, what are the properties of this emission? I'll get back to this in a minute. Let me just say that the reason why it hasn't been identified before in all the simulation is lack of resolution. You need high enough resolution to actually resolve this current sheet and see its collapse to plasmoids. And there is a very nice resolution study in this paper by Ripperda et al., where you can see the details, which shows that if your resolution is too low, you actually don't see this process. I mean, you see accretion, you see the current sheet, but you don't see this quasi-cyclic behavior. Okay, so let me go back to the current sheet. The question was, what is the nature of the emission? And the short answer, we don't know. And we don't know because we don't actually have a handle on the multiplicity. As I said, in the simulation, it is set to some floor value, which is very large compared to what we expect. But what you can do, you can make some simple estimates. So for example, the mean energy per particle in the current sheet can be very large for pairs. It scales inversely proportional with the multiplicity. And you can also estimate the synchronous cooling limit. It comes out to be this number here. And so you see that if the multiplicity is smaller than this value at the bottom, then particles in the current sheet will accelerate to this cooling limit. And in this case, you expect to have sub-GeV emission by the synchrotron process with quite substantial luminosity, roughly, let's say 10% of the Black-Fosnaich limit, as estimated in those papers. And on top of this, the accelerated particles will inverse Compton scatter soft photon from the disk, and you can have an even much higher emission. And if you, for example, take M87, you take some estimate of the magnetic field, say between 10 to 100 Gauss, you can have a few TeV, emission at a few TeV. So the luminosity here will depend on the details of the soft emission from the outer disk. So this suggests that in principle, we can have flaring, high energy emission flaring states from these accretion episodes that can actually explain, say, some of the emission in misaligned blazars and maybe also in blazars. But again, the key parameters that determines this is this multiplicity. If it's too large, the emission will come out in a much softer band. And so it's really desirable to try and find out more realistic values by other means. Okay, let me move on now to discuss the issue of plasma injection. And first, let me explain why this is an issue. This is a bit different than what you know from pulsars, because the black hole horizon is actually something like an asymptotic infinity, if you wish. And the point is the following. Once the black hole is activated and produces this very nice jet or outflow, you can show that plasma beyond the outer light cylinder must be flowing outwards, whereas plasma within the inner light cylinder must be flowing inwards due to the immense gravitational force. So there is a continuous loss of plasma from the causal region of the magnetosphere, which is located between the inner and outer light surfaces. And this plasma needs to be replenished if you want the black hole to remain activated for a long time. If it's not replenished, then over about a few dynamical times, the plasma will disappear and it will just form a vacuum state. And the question in this business is, how the plasma is injected in reality. As I said, in GRMG simulation, it is put by hand. So you might think that since we need really tiny amount that, and we have this dense accretion disk, it may not be a problem, but actually it's not so. First, you can show that charged particles cannot cross magnetic field line. Diffusion time is extremely long compared to the accretion time, so that doesn't give you anything. You might have some macroscopic rearrangement of field lines if you have some more complicated topology, which can inject plasma. But even this is not guaranteed to screen out the magnetosphere if the location of the injection does not comply with what is required, and if the timescales are not appropriate. And we're actually now studying this using peak simulations. What we find is that even if you inject a lot of plasma, you still find unscreened region of the magnetosphere. Okay, what we actually do understand better in this business is a mechanism by which you can produce electron and positrons by gamma-gamma annihilation. So this, of course, requires emission of gamma rays, MeV gamma rays from the accretion flow, and that's probably relevant to so-called RIAF systems in which the temperature of the accretion flow may be high enough. So what happens in this case? You have photons coming from the outer disk, they collide above the polar region and inject continuously per plasma. The question is whether the, sorry, just a second. The question here is whether the intensity of the gamma ray is sufficiently high to provide the density required. So I tried to estimate this with Frank Rieger in the paper. And what we found... Okay, what we found is that the multiplicity is very sensitive to accretion rate. And also for M87, we found that it's actually insufficient to screen out the magnetosphere, but there is a huge uncertainty in this estimate, and it's somewhat controversial. There is another group finding a larger values, but I think we all agree that it's highly sensitive to accretion rate. So obviously at some accretion rate, this process will not help much. So the question, what happens when you cannot screen out the magnetosphere? And in this case, what happens is that the magnetosphere becomes charge starved and develops vacuum gaps. So a vacuum gap is a region where a potential, electric potential is formed along magnetic field lines. Okay, so E dot B, the relativistic E dot B is non-zero. And once such a region is formed, it acts as a linear accelerator. It really accelerates particles like crazy. And these accelerated charges, on the one hand, emit curvature radiation, but at the same time, the inverse Compton scatters soft radiation from the disk, infrared or microwave radiation from the disk, depending on the details. And so they produce, as I'll show in a minute, they produce TeV photons, and these TeV photons, on the other hand, interact with the soft radiation to produce more photons. So the bottom line of this is that once such a gap opens up, it triggers a discharge process in which intense performation kind of screen out, provide the plasma needed, maybe in bursts. But at the same time, the radiation below the per production limit is released. So if you make some simple estimates, like in our paper, for example, you can find that a curvature emission, for example, in M87, let's take it as a canonical source, curvature radiation is released or actually peaks around 1 TeV or so, whereas inverse Compton emission peaks at higher energies, between 10 to 100 TeV, depending on the parameters a little bit. And so you see that these gaps can be quite efficient TeV emitters. Of course, the question is what's the luminosity of this emission? That will depend on the regulation of the gap. And I forgot to mention that these gaps are regulated by the production process. If you don't produce enough plasma, they will be huge and will lead to excessive plasma production. If you produce too much plasma, they will be too small and will not be able to accelerate particles. So there is a regulation process. So to study this more quantitatively, Benoit Cheruti and collaborators, Kyle Pefres, Asa Pilipov, developed a tool, a general relativistic peak code. This code actually includes also a module to compute radiation processes using Monte Carlo approach. In particular, it computes inverse Compton per production, etc. It also computes curvature emission and feedback. And there is a 1D version and 2D, 3D versions. In 1D, you can resolve the skin depths for realistic parameters. In 2D, it's not possible. I won't go into this technical detail, but let me show you an example of what's actually happening. So I'm showing an example of 1D simulation, 1D gaps. In this example case, what we do, we look at the particular magnetic field line, as you can see here, and we assume that initially some region along this line is devoid of plasma. So that's what you see in this initial state. So there is no plasma. We solve Maxwell equation to get the electric field, and then we inject photons. So the yellow line shows the photon content. We inject photons with high enough energy to start the spark process. And this is what happens. You can see that very quickly, electron and positrons are produced. The electric field is screened out. And actually, let me move it faster. It's to zoom up on the field, it's not really completely screened out, but it kind of undergoes plasma oscillation, electrostatic oscillation. And this oscillation accelerates particles and produce pairs and photons. And the amplitude of this oscillation is regulated by this process. And here you can see the yellow line here is the spectrum of the photons emitted from the edge of simulation box. And as you can see, it peaks at a few TeV in this case. And what we find is that you can, depending on the intensity of the soft radiation from the disk, you can radiate, say for a source like M87, about 1% or slightly less of the jet power. And this is enough to explain M87. Okay, sometimes you also see this quasi-periodic oscillation of the gap in 1D, but I won't go into this. Now, as I said, these 1D gaps are local structures. We don't see feedback on the global magnetosphere. So to study the global evolution, Benoit and his colleagues developed this 2D code. And I have to move on. So let me just quickly say that in this case, what they actually do, they study the global evolution of the magnetosphere. There is no realistic disk here. It's given as a boundary condition. But anyway, the bottom line is that they also find quite intense high energy emission from these structures. And that depends on viewing angle in this particular case. There is contribution from the current sheet and the equatorial plane, and a contribution from the polar gaps, spar gaps. So the red line here is what you see if you look at relatively small viewing angle along the axis. In that case, the emission is dominated by the spar gaps. And here is what you see age on. And you can get between 5% to maybe more of the Blunt-Wozniak limit in this emission. So under this condition, you expect to have very high energy emission from these gaps. Okay, now in the time remaining, let me quickly discuss the dissipation of the jets. So, so here, there are actually two scenarios for jet formation. In the first one, jets are formed by large scale or ordered magnetic fields, like in the simulation I showed at the beginning. Now, this is, in this way, you can actually form very efficient jet production. You can have very efficient jet production. In fact, you can have jet powers larger than the accretion power. But the question is how the field dissipates, as I mentioned, and you have to rely on relatively rapid growth of some instabilities. You can also convert magnetic energy to kinetic energy by image deacceleration. I'll make a comment in a minute on this. In the second scenario, the idea is to advect small-scale fields, magnetic loops, like what we see in the sun, into the black hole. In this way, you can produce a quasi-striped configuration. This is very good for dissipation, but the question is whether can you actually form sufficiently powered jets in this way. So I want to discuss quickly these two scenarios in turn. Let me make a comment about image deacceleration. So as I said, you can convert magnetic energy to kinetic energy if you have differential collimation. under which condition the jet is accelerated. However, as shown in this paper, and in particularly in this seminal paper by Yuri Lubarsky, the best you can do is reduce sigma to order unity, and even for this you need special conditions. More likely you will reduce sigma from something very large to something on the order of a few. So if shocks are indeed the channel through which the emission we see is produced, there needs to be some intermediate stage in which you dissipate the magnetic energy by other means to reduce it from sigma of a few to small sigma. And this has been discussed, for example, in this paper in the context of the extreme TV blazars. And so the conclusion is that in any case, you need some instability to develop. So what might be a candidate for instability? So the leading candidate, which has been discussed for many years in the literature, is the kink instability. And this instability is triggered in helical magnetic structure, like you see here, under certain conditions. And in the last decades, there have been some dedicated studies of this instability by different groups. And with the exception of one simulation, which I'll discuss later, all of these studies are not considering a realistic jet, but some so-called equilibria configurations, cylindrical equilibria configurations, which are quite optimal for the kink to develop. So the main question you want to answer is, first, how long it takes to dissipate the field, and second, what is the particle spectra producing this? And for this, you need peak simulation. So there are also some recent peak simulation of the kink instability, and I'll show quickly some results. Okay, so sorry, what's going on? Okay, let me show you a movie which I got from Anna Chashkina, with many thanks. This is a work in progress by the group of people listed here. It will be published very soon, I guess. In this case, you see a development of kink instability in a rotating cylinder, which is in previous simulation used a non-rotating cylinder. And it goes like this. So here on top, you see the time. Let me try and, yeah. So as you can see, it takes some time for the linear stage to build in. And then at some point, the instability becomes nonlinear. Come on. And you see now. And then it starts destroying the magnetic field in the core region of this configuration. And as you can see, after a while, it starts developing turbulence, and also some reconnecting current inside. And this is how the field eventually dissipates. And as you can see here, it takes hundreds of crossing time to actually destroy the field. And one important thing is that this kink instability doesn't really completely kill the field. It eventually stops when a new stable configuration is formed, at least in those simulations, with sigma of order unity. Now, what about the particle spectra? So there is one peak study by this group, not for the rotating case, but for the non-rotating case. And to make long story short, what they find is that the particle spectra here are either thermal or have very steep slopes. And the reason, according to these guys, as I understand it, is that this kink process is slow. So the turbulence it develops is relatively low amplitude turbulence with strong guide field. Okay, now let me just say a couple of more things about turbulence. So we had a very nice talk, if I remember, by Martin on turbulence. And what he showed is that, he showed results of dedicated simulation. Most of these are local simulations in local box. And what he showed that under certain conditions, people do find a hard parallel spectra produced. But the bottom line of this story is that the outcome depends on various factors, in particular the particle distribution function and the emitted spectrum. And these factors are first the amplitude of the turbulence. So you see here the dependence of the power law slope on the amplitude, which is defined as this delta B over B of the initial state. You see when it's smaller than unity, the slopes are very steep. And this is actually, this is consistent with the result of this global peak simulation. And it also depends on sigma. But most importantly, it depends on the way you generate the turbulence. So you can actually get different outcomes if turbulence is generated by different ways. It also depends on whether cooling is strong or not. So you see here this connection between what I meant between the global scale and the local scales. If you want to produce something like this with some instability, it has to be probably somewhat different than this kink. Okay, I think this is still open. The other thing other question you can ask is under which conditions the kink instability goes in the first place for realistic jets. As I said, what I showed you was for cylindrical equilibria. Now, there is one global simulation by Bromberg and Tchaikovsky that tried to study this with some limitation. And you see it here. And the conclusion from this study and also some other studies by other people is that the instability favorably develops in a refocusing nozzle or kilomashing nozzle like the one you see here. This simulation was done in the context of gamma ray burst, but if you go to blazars, then we have example of such collimation nozzle. For example, the edges T1 in M87 mentioned by Paulo, but they are located very far from the engine typically. So I don't think that this can explain the dissipation we see on much smaller scales. Nonetheless, instability can also develop if the jet is collimated in what Yuri Libarsky calls an equilibrium collimation. That requires the collimation profile to be at least parabolic. So you can make a very naive estimates by assuming a cross-sectional radius at onset to be, let's say, a few times the light cylinder of the system. And let's say adapting a gross time of, let's say, 100 crossing times in the covering frame. If you do this, you get gross lengths of 10,000 RG, and this is an optimistic estimate. This doesn't take into account the fact that the cross-sectional radius increases over the scales and other factors. You can also try to do this for M87 by looking at this collimation profile. This is the only source I know of where we have a very nice collimation profile from roughly 10 RG all the way to very large scales. And if you, so you see there are large error bars for the data here, but if you just naively adapt the profile they suggest in this paper by Hada et al., then you see that the jet starts roughly conically here, and then it undergoes parabolic collimation roughly. And so here the onset is likely to be on this scale, which is roughly 100 gravitational radii. Anyway, if I plug numbers here, I get gross lengths of about, actually by gross lengths, I mean dissipation lengths, not necessarily linear growth rates. I get dissipation lengths of, I don't know, 100,000 RG, already near the HST1 node. And I don't think this can explain what we see in M87. There is one caveat here, which is that if you look at the images and also at the velocity map, and I'm showing here the data from Mertens, you can figure out that this jet is stratified, as you can see here. There is a mildly relativistic schist, which actually accelerating if you look on larger scale, I'm showing here. And then you see also some blobs which move superluminarly, probably emitted from the inner core. So this structure seems to be more complex than the structure I assume for the naive estimates. And I guess it's probably desirable to try and study instabilities for these more complicated structures. Okay, so maybe that can help save the day. The other scenario I want to discuss is the one I mentioned for quasi-striped jets. So the idea here again is to advect these loops. And actually, to me, it seems more natural to have this structure, like what we see in the sun, for example, and stars. And in that case, if the loops have alternating polarity, then you will get a quasi-striped jet, as you see schematically here. And of course, this is very good because you have these current sheets embedded in the jet already from the beginning. But the question is, how powerful this jet can be. I mean, the idea of this structure dates back, I guess, to Romanova and Lovelace and many papers following this. So there has been a very nice study recently by Kyle Perfrey and collaborators. They did 2D simulations, force-free simulations, where they tried to actually explore this. And what they did, they advected magnetic loops with alternating polarity into the black hole using an artificial disk, which set as a boundary condition, and follow the evolution. And what they find, to make long story short, is that at least in 2D, you can actually form these mini jets with alternating polarity with quite substantial mean power. And when I looked at this paper, my reaction was that this will go away in 3 dimensions, because here it's supposed to be axisymmetric. So eventually, Jens Malmal did a 3D simulation of the same process. And to our surprise, we found that even in 3D, you still see these mini jets forming. And the mean power can actually be quite high. It can range from 10% of the maximum Blanford-Nayak power to something larger, depending on the conditions, provided the loops are not too small. And so this force-free study suggests that it's possible actually to form such striped jets. However, as I mentioned, these use some artificial disk. So the question that I was interested in was what happens when you do GRMSD simulations. And so we tried, so it's pretty challenging here because the simulation, it doesn't have appropriate boundary condition. It's just like a transient simulation. You put initial state and let it run. But we tried a simulation with, let's say, the one I'm showing here has 3 loops initially, rather than the one big loop I showed earlier. And the loops have alternating polarity. So you can see the solid line marks 1 polarity, the dashed line, and the opposite polarity. And then you let it get accreted into the black hole. And you see here the movie. So you see the first loop comes in and produces a very nice mini jet. And then it keeps coming in. And then at some point, the next loop coming in, you see the dashed lines here. At this point in time, there is no flux on the horizon, so the jet ceases or actually becomes weaker. And you can see a lot of dissipation in the current sheets. You can see it better here in the interface between these 2 loops. So the loops interact. You can see a lot of dissipation here. And then if you continue toward the simulation, you see that eventually the second loop takes over and you have another mini jet with opposite polarity. So you can form these jets, striped jets, even in GRMSD, but it's inconclusive because we eventually run out of disk and flux. And if you compare the efficiency of jet formation of the 1 loop and 3 loops, namely ordered field, you see that it's indeed smaller than the ordered field case, but it's still can be quite substantial. So I think the jury is still out. We need more efforts to say something more conclusive. And also we are trying not to do this with cooling. That might actually have an important effect. But it seems like this option might actually be possible, at least for certain regimes. And as I said, this can greatly alleviate the dissipation problem and also the loading problem, which I haven't had time to talk about. So I guess I'm over time. Maybe I'll skip the last part of this, what I meant to say, and I'll go to the summary. So I think that my conclusion is that these systems seem, at least the recent studies that I showed, shows that these systems are highly dissipative, not only in the jets, but everywhere. You see dissipation in the accretion flow, and maybe in the inner jet region, in the inner magnetosphere, maybe by spark gaps. And this dissipation can actually lead to very high energy emission from these regions, which might explain some sources we see, emission from, let's say, misaligned blazars or even blazars. Also, we still don't have a complete picture of the dissipation of the jet itself. Obviously, most of the emission in blazars probably come from the jet. And so I think that maybe the near future will shed more light on this. But at least my conclusion is it's quite challenging, actually. So far, I don't think that any instability was identified. Could be, again, due to lack of resolution or limited size of the simulation. Or maybe it doesn't exist. And so, as I suggested, maybe striped jets can do the work. And actually, we don't really know what the actual states. So I guess maybe future observations of these regions in M87 might reveal actually more information regarding the topology of the field. Okay, so I think I'll stop here, and maybe we should have some discussion. So thank you.
Thanks very much, Amir.
Yeah, that was a very nice review. So do we have any questions? Raise your hands if you do, I guess. Okay, so we have a question from Valenti. Yeah.
Yes, hello, can you hear me?
Yes, sure.
Great talk, Amir, thank you very much. I have a question because you were exploring scales which were quite different. So at some point, even you were mentioning regions which could be like thousands of gravitational radii. So what do you think in the context of your talk, all the things you were discussing, what do you think is the role of the environment? Because on one hand, you may have easily like quite dense inhomogeneities in the region surrounding the base of the jets. You have stars in different stages of evolution, like shedding quite a lot of mass in their surroundings, even some massive stars. So what do you think the role of the environment in the context of your talk?
In the context of blazars, I'll say, because that varies from, source to source, from geobusiness. In blazars, so first of all, the environment may have important role in collimating the jet and also, accelerating it by this image deacceleration process. And actually, it could be that we have sufficiently intense disk winds. Some people seem to find something like this, but that's unclear yet. But otherwise, we do see this collimation, at least in M87 and some other sources. So I think in this region, it must be related to the environment. And unfortunately, I think it's in M87, it's unresolved below the boundary radius. So you don't really see how the density profile looks like below this. But it's quite clear that it's pretty flat near the boundary radius. And this, for example, this could be the reason why the HST1 is produced. And there are a couple of papers on this, in the literature by different people. On larger scales, if you look at M87, the jet appears to be, at least last time I checked, appears to be quite conical. So it doesn't seem that, as far as interaction with the jet is concerned, it doesn't seem that the environment has great effect, on the jet, judging by this collimation profile. Maybe, it can trigger some instabilities. I don't know, to be honest. This is something that I think it has been studied by some people, but at least in the linear region. So that's what I have to say in context of blazars. And of course, once you have interaction with the jet, then it might be very important, as I said, both for triggering instabilities and for the dynamics. For example, if you have intense environment and you get this collimation nozzles on small scale, so this is a very different picture than what I described here. Then you can do all kind of other things. You can actually dissipate the energy there, maybe. In other sources, it's very different, But that's my understanding from blazars, at least.
Maybe for Yuri's question, yeah, in simulation like Quasistriped had a lot of recollimation shocks, and there's stationary features sometimes. So the environment maybe can impose. What do you think about that? The environment imposes a region where.
But I'm not. The simulation I'm aware of by Quasistriped, they either have a wall.
Yeah.
They have some artificial boundary. So. And also the one which you are referring to, I think, are hydrodynamic simulations. They are not high sigma.
Yeah.
Okay, that's a different story. Okay, I have a lot to say about hydrodynamic jets, but then the question, how do you produce a relativistic hydrojet in blazars? You must have some sort of magnetic extraction. Maybe not, but then I don't think anyone understands how to do this. In GRBs, you can rely on neutrino annihilation, and that might produce enough power, although recent studies show that it may not actually.
Okay, all right. Yeah, Yuri, you got a question?
I was just wondering if one were to accept your suggestion that without this striped jet configuration, you can't have very effective dissipation in a jet. But on the other hand, I think there is some evidence that in some systems you have this mad state where you have very ordered magnetic field, obviously, probably comes from larger scales. Is there any evidence?
So how do you know this? This depends on some estimates of the accretion flow, which you don't really know. It's model dependent, I don't know something. Some direct indication, right?
So you don't believe in polarization from M87 as the evidence for this type of states?
I'm not saying that I don't believe, but I'm saying that it sort of involves, it's model dependent. It involves some modeling, right? And actually, Roger just put a paper out a couple of days ago where he claims that all this is nonsense, and the actual, there is no big torus accreting. There is a completely forceful magnetosphere. I'm not sure I understand the details, but so and he has a valid point. If you look at the EHT data. By the way, as far as I understand, because the EHT image is very tricky, because what they do, they have to cut the inner region of the jet because of this floor density issue. I asked them once to send me an image which is produced without cutting this. I don't know, I didn't get any reply. But so it's not like you do a simulation and you have a very nice image. You do a lot of things. You have to assume something about the electron temperature. So they have this prescription, which is maybe reasonable, but if you look at the paper number 5, this rejection table, it's actually quite tricky. And so I would be rather careful with this conclusion. And I think the point by Roger was that if you take these estimates, you find that the pressure of the emitting particles is like 10 orders of magnitude smaller than the magnetic pressure you estimate from the jet, because we do see a jet, and that is within the simulation of the EHT people, right? And he claims that it's just unlikely that you will have so little pressure in these emitting particles. That's his motivation. I'm not sure I agree with this, because I think that they did look at this. And I think what they claim is that the ratio of the kinetic to magnetic pressure is very sensitive to magnetic field. And it could be that there is a magnetic field profile, but this is an issue. And so so I'd be careful with these estimates, but I'm not ruling out match states. I'm just saying that if this is the case, we need to try and identify, how dissipation works.
Let me try to ask this question backwards. Suppose nature finds a way of concentrating magnetic field of the same polarity on a black hole. And suppose you do make a Blandford-Snarek jet, but it's not very effectively dissipating energy inside it. What would be the observational appearance of such jet? And is there any, can you think of any evidence?
Yeah, the first one will be very little efficiency of gamma ray production. You will see, if you look at these lobes, hotspots, and you make some estimate, of course, you can always say that this is a very local time, but if you believe that the mean power reflects something, so from these, the lobes, you can estimate the mean power. That's what people do. You will find it to be larger by orders of magnitude than the typical gamma ray emission you see, even with beaming, but let's say after correcting for beaming. So that's not what is seen. What is seen, according to different studies, is that radiative efficiency is very high. It's pretty high.
Mm-hmm.
So you might argue that maybe dissipation occurs on larger scale. That's a possibility. But then I don't see how you can explain the variability we see. If it occurs, let's say, on kiloparsec scale, I don't know. You dissipate the energy, let's say the HST 1 node, that's possible. Then, you have an issue with the variability. The TV emission, TV flares have duration of 1 RG roughly in MT7.
Mm-hmm.
So, or maybe we are missing something.
Okay, thank you.
But I think maybe this is where the multi-scale nature comes in, or they're FR1 and FR2 galaxies. The FR2 argument has a lobe that works, but in FR1s the jet dies and seems to be transonic and gets mass loaded maybe, so it's not so clear. And also the disk environment is very different in FR1s, like M87 is RIAF or whatever, so it's a very tenuous kind of atmosphere. Other like powerful quasars, flat spectrum radio quasars probably have huge accretion disks that could even be self-gravitating, at least if they're like some quasars.
Well,
the environment could be very different, and maybe the results, like you said at the beginning, maybe which process dominates whatever depends on the environment and the field configuration. And
I think that the dichotomy to FR1 and FR2 is more related to the jet power, because first of all, from theoretical point of view, there are some papers by different people, both for hydrodynamic jets and magnetic jets, and they show that once the jet power drops below a certain value, if you take a typical galaxy, then you get an FR1 source because the jet cannot break out. It's like a breakout of. So in that case, you get the FR1 source. And I think it's also consistent with the observation because the FR1 are systematically less powerful, right, than FR2.
Yep.
And that actually depends only on the power, not so much on the detail, if it's magnetic or not. And I think that's probably the issue here. But if you look at FR1 sources on parsec scale, they look, like FR2, right? On parsec scale, they are relativistic.
Yeah, but they're like the TV blazers, maybe it's orientation effect, but all look more non-relativistic. Like the BLX, whatever that means, historically had a mean Doppler factor of 4 less than 10, and the FR2s had higher Doppler factors.
Yeah.
Selection effects and stuff like that in there, but
that's I agree. That's a puzzling. That's the the so-called Doppler factor crisis.
Yeah.
And the Watson models must have very high Doppler factors. So the consistency. So yeah, that's interesting, indeed.
Yeah, but I don't know the answer. Yeah, but okay, Felix, you got a question? Yeah, let's see. Oh, hey Felix.
Yes, yeah, thanks. So question is the following: your discussion was around M87 basically. So that was for a purpose, or because
no,
you consider M87 as a example of other AGM blazars, or it's some exception?
No, I don't think it was around M87. But M87 is the only sort where you actually have data that with resolution to probe scales from roughly the horizon to outwards. But I have some other examples. Usually, I mean, there are correlation profiles for some other sources, but they don't go down to these scales. The kind of resolution is, let's say, 100 RG at best. So you don't really know what happens below 100 RG in terms of correlation. But some of my estimates were actually quite general, not only related. The one thing which you might be right is that I think that in blazars, at least powerful ones, the accretion rate is in a regime where you expect to have a thin disk form, not this torus, not the other for IF. In this case, it's quite little is known from a theoretical point of view. It's because, to do this simulation is very difficult. You don't have self-consistent radiative cooling in the simulations. And even if you do, there is not sufficient resolution to resolve the disk. So I know that there are attempts in other contexts, I think maybe by Gemstone, but so that actually is another issue, which, I mean, I don't even have much to say about it. But, the IF sources are more like MT7, I guess.
Yeah, I agree that is the best source from point of view of resolution of spatial distribution, spatial resolution. But there is a timing as well, and the variability you discussed, you mentioned, it matches, I mean, the magnetosphere scales. But if you go for the variability for other objects, you mentioned 2155, the same is for the C279, then the variability is less than RG over C.
Okay, that's,
Do you have explanation for that?
Yeah, okay. This is based on estimate of the black hole mass. So how do you estimate it? From the sigma relation? I accept this estimate. Even though, the scatter is 3 decks, if I remember, but, for one source, who knows? So there is an uncertainty of a factor of 10, at least in my opinion, just from the estimate of the black hole mass.
Probably not for 155.
No,
you could not also for C279. I think that the number.
Yeah, 3279. I think you have lines, so you can use this reverberation mapping scaling. Maybe it's a better estimate.
Okay. So the answer is, so in order to survive, I mean, this concept for these powerful blazars, then you assume that black hole estimate is, the black hole mass is overestimated.
No. I'm willing to buy. I don't have a good explanation to this very rapid. Let me, okay.
So if mass uncertainty, yes, okay. We could
what's the amplitude of this very rapid fluctuations?
The minutes.
No, not the time scale. What's the amplitude?
It can be factor 2.
You could see that factor of 2, 3.
Factor of 2. Yeah, that's substantial. So maybe that means that you need if it's from the magnetosphere, then you need some small patches. And then I don't really have a good explanation. I think that there have been other ideas like jet in a jet. But yeah, that's puzzling. But it's only like 1 or 2 sources that you see this, right?
Well, even one is sufficient if we trust this black hole mass estimate. So that was actually my question. So could we introduce in your concept the
if it's 1/3 of the horizon, it's not a big, if it's 1/3, it's not a big problem. If it's 10 to the -2, it's a huge issue. So, I mean, I guess.
But you could incorporate this kind of jet in the jet type of idea. I guess not, right?
Okay, that's I didn't have time to. In the context of striped jets, this is something that can happen. Provide, the idea there is that you have reconnection and then the plasmids themselves move at a velocity of roughly √2 sigma. And this is still a question if this is indeed occurs when you look at macroscopic scales, because all current simulations suggest that it might happen. The traditional peak simulations did not show actually this motion, but maybe it happens. So I think that then it's possible. If you have ordered field, then you need some, then I don't really see, because from turbulence, I'm not sure you will get something like this. I can imagine this if I have these big macroscopic current sheets produced, for example, for a striped jet, maybe, but I don't know. I just don't understand this. So yeah.
I agree. Yeah.
Okay, thanks.
But by the way, what's your estimate for the scale here compared with the dynamic horizon time scale?
What do you mean, for which object?
At 2155.
Well, I mean, in my memory, I mean, if it's less than a factor of 20 to RGO.
Okay. Okay.
So yeah, it's quite big. I mean, so it's something should be invoked, because hardly could make such a. Well, I agree. This mass estimate of the mass is another issue, but and I'm not an expert at all, but these AGM people are so confident.
I'll be much more comfortable if I see a sample. Give me a sample of 20 sources to show this variability, and then of course you have statistics. It's unlikely.
But why you need 20 if 2 deviates? If you are believing one, why I need 20?
Because for one, I can question this estimate of the mass.
Okay, so that is the point. So
for a sample of 20, you have the scatter, and then it will pin it down. So
yeah. Oh, okay. Maybe I was not correct writing the scales. So I meant the variability scale is less than RG over C by a factor of 20. For 2155.
And what's the uncertainty in this estimate?
Oh, that is, I don't know. If you ask AGM people, they say it cannot be more than factor of 3, 4. So they don't believe that could be order of magnitude uncertainty. But this is not my opinion.
Yeah. But if you go a factor of 4 from 20, then it reduces it to like 1/5. This is still an issue, but it's with this you can maybe work. I don't know, but I agree. This is a very puzzling data.
And that is coming. I mean, for example, if you have more sensitive instruments, that is in future is coming. So that my question was, is possible just somehow incorporate into this magnetosphere concept something like reconnection, which leads to the jet into the jet kind of. So in other words, to produce in magnetosphere kind of moving blobs or something like that, which could explain. That was
again, this is a problem of the multiscale. I mean, you cannot have you cannot have one simulation that resolves the global scale and the macroscopic scale. So you have to do something. And I think that maybe some people here can remark, but maybe there are attempts to, I don't know, to somehow overcome this, to use this microscopic models, subgrid models. But I don't know. That's the issue. That's the challenge I was mentioning. If unless you resolve the skin depths, I will be very skeptic about such a simulation. So I've showed you the dynamic range that you need. It's
yeah. Okay, thanks, Amir. Thanks.
Any more questions so far? If not, I'll take the prerogative and ask one about sort of the inner magnetic field condition. So a lot of people used to argue in the old days, and I heard it less, but that the interchange instability, when flux lines go through, would completely destroy the field or set the rate at which you can pilot field. So the MAD solution wasn't robust depending who you talk to. And has that changed or technically?
Yeah, that's what Roger claims in his paper from 2 days ago. Actually, so I don't know. I mean, but the simulation that I showed you is the simulation. I don't think you see something like that. What you see in those simulations in the MAD state, you see this quasi-periodic behavior. I don't see, the main feature we see there is this current sheet. And actually, I think we understand this. So, the studies you mentioned were before, I think before the simulation had enough resolution to do all this. But actually, what Roger claims is that, the simulation is too limited and, we just cannot simulate the configuration you envision. So it's a fair, I don't know.
Yeah. And does 2D versus 3D matter? I would have thought like reconnection seems topologically is different in 2 dimensions versus 3 dimensions. There's a lot of argument. So, but you said Rupert's simulation matches your 2D one more or less. I might have expected some qualitative change or things happening.
Yeah, there is qualitative change, but it's not dramatic, I think, in terms of reconnection rate. That's what's important. The reconnection rate appears to be roughly the same. Now, I didn't want to go into technical details, but there is one subtlety here is that in image simulation, if you have a high enough resolution, the reconnection rate saturates at a value which is lower by a factor of 10 than kinetic simulations, for reasons that I don't think is well understood. But I'm not an expert in this, but and apparently, maybe Yuri Lubarski can comment, but apparently that's what people see in the discussions. Apparently, the kinetic physics is important in this. So what you see in our simulation, the timescales are not exactly. If you do if you correct it for this reconnection velocity, then this flaring state will be shorter by a factor of a few roughly. So that's but I mean, other than that, I don't think that, anyway, you can look at the paper by Ripperda et al., which they do 3D simulation, and it seems like a very similar behavior, actually.
Okay, Yuri, did you have a question?
I had exactly the same question about 2D versus 3D, that 2D conserves flux exactly, but 3D, the flux has a way of escape.
So you do see, in 3D, you do see a structure, you do see these spiral arms in structure, but as far as the global behavior, if you, don't care about these details, it's, you still see this quasi-periodic oscillation, this quasi-periodic behavior. You still see the reconnection, the current sheet that reconnects. It's very similar in terms of this gross properties.
It is a little bit different that in Ripperda's simulation, at least that's my impression of it, when the flux escapes from the black hole, it does it mostly to one side, so this m equals to 1 spiral arm. So
yeah, that could be. That could be. And so, also,
in a sense, my impression of Ripperda's simulation is that they don't really in 3D significantly halt accretion, for example. It's just that.
No, but if you look at the plot of if you look at the plot of the accretion rate, mean accretion rate in their paper, you still see the modulation. It's true. The modulation of the m dot are less regular and have lower amplitude. We find amplitude of factor of 100. They find factor of 10. So it's, but it's still substantial. It's not, it's very different from the low resolution simulation. And I think their resolution study is very interesting. You can see really differences when you increase the resolution.
Any other questions? We have like 5 minutes left. Not having yet another question. Since you're studying the field geometry near, what can you say about the Blandford-Znaic efficiency? Like there are arguments, how much power can you get out from the Blandford-Znaic mechanism? And can you power the radial lobes? And the answer, people say not enough, but it all depends on what's happening with the magnetic field near the horizon. So which your simulation in principle has something to say about. Where do you think that stands? What's the maximum power you can get out?
I'm not sure I understand the claim. You don't know the accretion rate. If it's not enough, just increase the accretion rate. What's the problem? I mean,
right, but people said that the field will saturate, and when you have a MAD configuration, that's the maximum you can get out, and it wasn't necessarily enough.
Yes, but that limit depends. So what people find in geometry simulation, roughly speaking, is that you can get up to 150%. Okay, that's what Sasha Tchaikovsky likes to advertise. 150% means 1.5 the accretion power. So the power itself will depend on your accretion, accretion rate. Now, if you have other observations, maybe for example, if you see also emission from the disk, and you have some other constraint, it's another issue. But and as I mentioned, these simulations are mainly relevant to IF sources. So then you don't even know what's the microphysics. I mean, it's this coefficient, the coupling between ions and electrons is not well known. So I think there is a certainty, but maybe, I don't know, maybe there are some. If you are referring to something new, then I may not be familiar with it.
No, it just, the simulations weren't really good enough to do the job before, and now the resolution has gotten a lot better. So you still think that can be very efficient in principle if you pile in enough stuff.
So if you do a MAD state, yes. If you do quasi, what I said, I kind of find even if you have loops, by the way, if they are big enough, you can actually get a MAD state. But if they are small as the one I described, it sort of depends on other, it depends on other factors. In particular, I think cooling can be very important. Now people start studying this, but then it's still the question if the jet power produced by this process are powerful enough to explain sources. I don't know. They are not negligibly small, as I showed. You can have 10%, but of course we still need to study it better. But that's I think if you have other field, at least in terms of power, it should be okay. And actually, in gamma ray burst, actually, it should be actually low. If you assume a MAD state, you get a huge power. But I think that's actually understood now. You don't have time to accumulate the field. But
okay. Should we stop, or let's see, or it's me or Felix? Maybe, okay, I'm talking too much. Well, I'll ask the very last question, then we'll stop. So back in the old day, once I proposed a stripe model, I got attacked because there's no way you can have these loops. It all depends on the magnetic field configuration that you put on the disk. So how do you argue for having loops? People would say it's a free parameter. You can put in what you want and you get out what you want. But
yes.
So is there a robust mechanism for getting seriously ordered loops versus lots of little small ones that bubble might not give you a lot of efficiency, like you were saying?
So, sorry, the claim was that you cannot have ordered field or small loops?
Or large, or domains with strongly ordered field to give you a very nice striped jet.
Yeah, I don't know. I don't think we understand this. We don't have enough physics to actually say something about this. And these simulations are very limited. You don't actually have boundary conditions. The only system where you can try and study is gamma ray burst. You start from a progenitor. Let's suppose you believe it. Even then, people, what they do now is they put the magnetic field by hand, but that's maybe for technical reason. But in AGN, we don't even know, how the matter arrives at the center of the galaxy well enough, not to mention magnetic field. So that's actually my understanding. I don't know, but there have been a few papers by Uzdensky and other people trying to study this formation of loops using analytic models. I think there is some insight there. And
okay, thank you. I guess it's now 10:30.
Hello?
Yeah. Yep. Go ahead, Felix. Go ahead.
Maybe it's it's too late, but just very brief question. So we know that the M87 could be a good object for X-ray particles to 10 to 20. And in fact, that is the probably only one. So we need a very large, massive black hole, right? Like 10 to 10 approximately. So in the case of these new studies you did you explore possibility of extraction protons to 10 to 20 in M87, or is just the old very general estimates from the first principles?
No, I didn't, and I'm not sure I understand your claim. I mean, it depends also on the magnetic field, right? You need to confine the.
No, but you know yourself. I think you also did that. So there's the mass of the black hole should be, if I remember correctly, more than a few times 10 to 9, in order to get 10 to 20 protons. I mean, I remember that it is what I'm saying is from your papers as well. And then
From my paper? Okay.
yeah, I forgot, but we did also from the research that I remember we arrived to the same conclusion. So, but anyway, so with this new developments, theoretical, whatever, did you try to return to this question of acceleration of particles to 10, 20?
No, I didn't.
Okay.
Okay.
Good.
Yep. All right. Any more questions? If not, I think maybe we should stop it. So Amir, thanks again for collecting this really good review talk.
Thank you for the invitation.
Yeah.
See you.
Just,
bye.
Okay, see you. And a reminder, the next talk is in 2 weeks, and we'll focus on the effect of the extragalactic background radiation. It absorbs the spectrum from these blazars and changes things, and you can learn lots of interesting things from that. So we'll see you in 2 weeks then. Okay, Yuri, any last words? Or
Bye.
No, thanks very much.
Okay.
Bye.
Bye.
Thanks, Amir. Okay, bye, everyone.
Thanks. Bye.